Okay, hello everyone. We're just waiting a few minutes for the rest of the class to join. Okay, we'll go ahead and get started. Today I'm going to review for the test. The test on Friday will be online. We will not be having a lecture. The test will be, I haven't finished writing it, but I anticipate that you don't necessarily have to begin it at 2 o'clock. There'll be an open time. There will be an expiration though, which you have to complete it by a certain time. Okay, so I'm going to go through and summarize.
Dr. Trump, I have a question.
What's that?
Is the test going to be given on the Pearson app, or is it going to be given directly on Canvas?
Probably going to be on Top Hat. But as I say, I haven't finished writing it yet.
Dr. Trump,
Yeah.
I've been having a lot of issues with Top Hat recently. Is there any way that I could take it on Canvas? Because, I just found out yesterday that there was, I guess, homework assignments or something that have been posted on Top Hat, and it didn't give me any notifications. So, I have a lot of anxiety about using Top Hat.
Okay. All right. I will send you out instructions as to where the test will be and how to access it.
Thank you.
Okay, I'm going to go through and summarize the main points. I know in the past when I've done test reviews, they were more interactive, and I'm hoping that future test reviews can be more interactive. But today I'm just going to go through and summarize. The test will cover chapters 1, 2, and 3. Okay, I'm not going to say too much about the fundamental structure of the atom. You should be familiar with the shapes of s and p orbitals. And what orbitals are, they're regions of probability for finding an electron. Okay, you should be familiar with what isotopes are. I probably won't ask you anything about electronic configurations. If I do, it would just be like one question. Okay, make sure that you know the difference between ionic and covalent bonding. Ionic bonding involves complete transfer of electrons. We have fully charged ions which are attracted by electrostatic forces. Covalent bonding involves the sharing of electron pairs. Be able to recognize or determine whether a compound should be nonpolar, polar, or ionic. Be able to draw Lewis structures or be able to identify correct Lewis structures. Okay, I would strongly recommend that you complete chapter 1 of Pushing Electrons. This is all about drawing Lewis structures, such things as formal charges and the octet rule. Okay, these are common bonding patterns. Okay, this will help you a lot as far as drawing Lewis structures. Carbon normally forms 4 bonds, nitrogen 3, oxygen 2, hydrogen, and halogens normally form 1 bond when they're neutral. Okay, some Lewis structures require double or triple bonds in order to complete the valence shells. Okay, we can estimate bond polarity by differences in electronegativity. The bond dipole moment is the charges times the distance between them, and it's measured in units of dBis.
I'm sorry, can you repeat that last part? The bond dipole moment
Bond
is what?
dipole moments include 2 factors, the charges and then the distance between them, namely the length of the bond. Okay, here's an abbreviated table of electronegativities.
We actually, well, at least I can't see the screen that you're going over.
Okay, let me double check here. Okay.
Dr. Trump, could you let Walin in?
Yeah, I did.
Oh.
Okay, let me try this once again. Okay, now I'm sharing this.
Thank you.
Okay. Okay, here's an abbreviated table of electronegativities. And if we look at the difference between electronegativities, kind of an arbitrary difference is about 1.9. Okay, for example, lithium fluoride, lithium is 1, fluorine is 4, that's a difference of 3, clearly much greater than 1.9, so clearly ionic. Okay, something like NO is clearly covalent. Okay, there's only a difference of 0.4. Okay, be able to recognize and calculate formal charges. Again, pushing electrons gives you a good review, a good tutorial about how to do that. Okay, the total charge on a molecule is the sum of the individual formal charges. In this example, this is an addition product between borane and ammonia. Overall, it has no charge, but nitrogen has a formal plus charge, boron has a formal -1 charge. Right, these are bonding patterns that include not just neutral atoms, but also cationic and anionic forms. Okay, for example, I'll just go through a few of these. Nitrogen, okay, as in ammonia, normally forms 3 bonds, has 1 unshared pair. The ammonium ion, NH4+, has 4 bonds and no unshared pairs. With oxygen, oxygen normally forms 2 bonds, has 2 unshared pairs. And a good example is water. If it carries a minus charge, you'll have 1 bond and 3 unshared pairs, as in the hydroxide ion. And then on the other side, we have something like the hydronium ion, oxygen with 3 bonds and 1 unshared pair. Okay, I'll definitely have some questions about resonance structures. Resonance structures only involve the movement of electrons, not atoms. All the forms must be valid Lewis structures. And if we have non-equivalent resonance contributors, we can determine which one has more contribution based on which structure has as many octets as possible, has as many bonds as possible, and has the negative charge on the most electronegative atom. Okay, it's generally better not to have charge separation. Okay, so here's an example of major and minor contributors. Okay, the form on the left would be a major contributor, since there is no charge separation. The structure on the right does contribute, but less so because you have a separation of charges. Okay, here we have the cyanate ion, and the major contributor has the negative charge on the oxygen, the minor contributor has it on the nitrogen. Okay, oxygen is more electronegative than nitrogen. Okay, and then here is example of charge separation versus no charge separation. Okay, so we move away from a negative charge, and there has to be an atom that can accept. Okay, as in this example. The acetate ion has two equivalent resonance forms, so they contribute equally. Okay, be able to draw and recognize condensed and line angle formulas. Okay, so I'm going to move through this fairly quickly. So these are line angle drawings. Okay, heteroatoms need to be shown explicitly. Double bonds need to be shown explicitly. You do need to show the aldehyde hydrogen here. Okay, otherwise the appropriate number of hydrogens are implied. Okay, just a few more examples of line angle formulas. Okay, I'm skipping over this, calculating empirical formulas. Okay, when we combine, for example, s and p orbitals, we obtain hybridized atomic orbitals. These are conserved. That means that however many orbital wave functions we mix, we get that many hybrids. Okay, for example, for sp3, we mix an s orbital with 3 of the p orbitals. So that means we're going to have 4 hybrids, 4 sp3 hybrids. Sigma bonding involves overlap of one orbital lobe. It's a direct head-on overlap. Okay, here's a sigma bond between hydrogen atoms. And this is the sigma bonding orbital. And then we also have an anti-bonding molecular orbital. Right, here is the electron paramagnetic map for the hydrogen molecule. Okay, you can have sigma overlap between p orbitals, 2 p orbitals. You can also have sigma overlap between an s orbital and a p orbital. Here we have constructive interference, which produces a bonding molecular orbital, and destructive, which produces an antibonding. All right, the other type of bonding which we'll consider in this course is pi bonding. where we have the side-to-side overlap of two p orbitals. Okay, when we have a double bond, one of the bonds will be a sigma, one will be a pi. The pi bond overlaps in two locations. Okay, so this is half of the pi bond, this is the other half. Okay, sp3 hybrid atomic orbitals will give rise to tetrahedral geometries. sp2 will give rise to trigonal planar, and sp will give rise to linear. VSEPR says that electron pairs are localized into orbitals and they repel each other. They want to get as far apart as they can get. Okay, an sp hybridized atom will produce a linear geometry, as in beryllium hydride, BeH3. Borane, BH3, would have a trigonal planar. Okay, there's no lone pair on boron. It does not have an octet. Methane is an example of an sp3 hybridized orbital. Okay, so this is a summary. The main thing I want you to be able to understand is to associate a hybrid with a shape. Okay, if we have a triple bond, we'll have 1 sigma and 2 pi bonds. Sigma bonds rotate freely, which gives rise to conformations, such as the eclipsed and staggered, shown here. You cannot rotate around double bonds. Okay, you actually have to break the bond before you can rotate it. Okay, we also had an introduction to isomerism. Isomers are compounds that have the same molecular structure, but a same molecular formula, but a different structure. And we looked at two main types of isomers, constitutional and stereo. Constitutional isomers are those in which we change the skeletal arrangement. So these are the 3 constitutional isomers of C5H12. These are stereoisomers. Okay, they are geometric isomers. The double bond, in this case, is in the same place. It's between the 2nd and 3rd carbons. This is what we call cis, where these 2 methyl groups are on the same side. This is trans. But both of these are constitutional isomers of this compound called but1ene. Okay, the double bond has been moved. All right, let's move on to chapter 2. Okay, acids and bases, functional groups is the subject of chapter 2. Okay, here we start out by talking about bond dipole moments. Okay, ethane is nonpolar, and as we go across this series, these become successively more polar. And then on the far right, we have an ionic compound, which involves even greater separation of charges. These are examples of bond dipoles measured in Debye's. Okay, notice here the CO double bond, CN triple bond have an especially large dipole moment. Okay, a molecule can have polar bonds and be polar or non-polar depending on whether these bond dipoles cancel each other out. So in the case of chloromethane, there is a very slight pull from carbon to hydrogen. There is a large dipole from carbon to chlorine. These do not all cancel each other out. So this has a molecular dipole. Okay, same way with chloroform. Carbon tetrachloride, however, has a zero dipole moment. Okay, these all cancel each other out. Okay, the molecular dipole is the vector sum of the bond dipoles.
I have a question.
Yeah.
So for the case of chloromethane and dibromoethene,
Dibromoethane.
yeah, sorry. In those cases, would those be ionic?
No.
No.
No, the difference in electronegativity is not greater than 1.8 or 1.9.
Okay, so in order for something to be ionic, it has to be greater than 1.9.
Yeah, the difference in electronegativity.
Okay. What about for covalent or not covalent? Excuse me. What about for polar and non-polar? Just to be clear, like what would be the range there?
Non-polar would involve an electronegativity difference, say, of less than about 0.5. Okay, in the case of carbon and hydrogen, the difference is about 0.4. Okay, so the CH bond is really non-polar. It's just very slightly polarized toward the carbon, but it's essentially non-polar.
Wait, so less than 0.5 is non-polar, and then
Yeah, between about 0.5 and 1.8 or 1.9 would be polar covalent. Okay, did that answer your question?
yeah, sorry, I'm just jotting down notes now just to make sure I have it.
Okay.
It's been a while since I reviewed that part, so I just wanted to be clear.
Okay, lone pairs of electrons do contribute to both the shape of the molecule and the dipole moment. Okay, so we have to take into consideration lone pairs. Okay. And okay, here we have some examples. These are all polar molecules. We have ammonia. Okay, this is water. Acetone. Okay, remember a few slides back we said the CO double bond had an especially large dipole moment. Okay, and then the CN triple bond is even larger. If we had something like, what's my chalk here? Okay, if we had something like this, okay, in this case, this should be actually, let's make that a triple bond so that it's entirely linear. Okay, so this is a case where even though we have these strong dipole moments, they would completely cancel each other out. Okay, so this would have a zero dipole. Make sure that you understand and recognize intermolecular forces. Okay, I'll be asking you about intermolecular forces. The three main forces that we talked about were dipole-dipole, London dispersion, and hydrogen bonding. Dipole-dipole interactions would result when we have two polar molecules. We have a permanent dipole in that substance.
That felt great this morning wearing it.
What's that? Okay, in dipole-dipole interactions, a good example here is chloromethane. Okay, these molecules behave like little bar magnets. Okay, I'm going to move along here quickly. London dispersion forces involve a temporary dipole. This is the main attractive force between nonpolar molecules. Branching lowers the boiling point because there's less surface area in contact. For hydrogen bonding to occur, you have to have an NH or an OH bond. This is an especially strong type of intermolecular force. When you have hydrogen bonding, one of the effects is you'll have a significantly increased boiling point. Okay, here we have, these have the same molecular formula, but a different structure. Ethanol exhibits hydrogen bonding, so it has a much higher boiling point. Ethanol and ethylamine both exhibit hydrogen bonding, but hydrogen bonds between OH groups are stronger than between NH. So this will have a higher boiling point than ethylamine. Okay, I'm going to move through this quickly. Like dissolves like, polar dissolves polar, polar dissolves ionic, like water dissolves sodium chloride. Nonpolar dissolves nonpolar because of the explanation that's typically given is there's an increase in entropy when these mix. Functional groups, this is going to be important. Make sure you know your functional groups, be able to identify them. Okay, I think that slide was out of place. We'll come back to that. Arrhenius acids, we're going to skip that entirely. Be able to recognize Bronsted-Lowry acid-base conjugate pairs and the definitions of Bronsted-Lowry acid bases. Acid strength, okay, the extent to which it ionizes. Okay, remember, the stronger the acid, the weaker its conjugate base. This is an important concept, and that is that when we have an acid-base equilibrium, it's always going to favor the side of the weaker conjugate acid-base pair. It always goes from stronger to weaker. All right, in this example, the pKa is larger, so water is a weaker acid than acetic acid, for example. The stronger acid-base pair and the weaker, stronger acid-base pair are always on the same side. The weaker acid-base pair are always on the same side. Okay. There's a solvent limit. The strongest acid or base that can exist in a certain solvent is the conjugate acid or conjugate base of that solvent. So for example, in water, the strongest base that can exist is hydroxide. If you put a stronger base than that in water, it's going to form hydroxide. It's going to remove a proton from water immediately and form hydroxide. Okay, these are some of the effects on pKa. One of them is electronegativity. As we go across a row, considering neutral species, acidity goes up. As we go down a column, okay, for example, the hydrogen halides, acidity goes up. Inductive effects, if we have nearby electronegative atoms such as chlorine, they will increase its acidity. Hybridization, okay, can affect acidity. Where we have this sp2 hybridized nitrogen atom, okay, that is a stronger acid than when we have the sp3 or tetrahedral. Okay, so the more S character we have, the more acidic. Okay, so a triple bond CH is much more acidic than if we have a double bond CH or a single bond CH. Resonance is a very significant factor in acidity, whether we have resonance or not, as illustrated by ethanol and acetic acid. In acetic acid, the conjugate base is resonance stabilized. We can spread out that negative charge. With ethanol, the conjugate base is not resonance stabilized, and so it is about 10 to the 11th times weaker as an acid. Know the definition of Lewis bases or nucleophiles and Lewis acids or electrophiles. Okay, we're going to be using those terms a lot, but for right now, just be aware of the definitions. Okay, functional groups, be able to recognize functional groups. Know the names of the first 10 alkanes and be able to apply the IUPAC rules, which is chapter 3, which is what we'll come to. Okay, so these are the various functional groups. Alkenes.
What specifically do we need to know about each group?
Be able to recognize it. Okay, if I show you a structure, what is the principal functional group? We haven't learned how to name these yet, but you know, if you saw a drawing of this, for example, okay, you'd say that was an alkyne. If you saw a drawing such as this, methylbenzene, I wouldn't expect you to name this, but be able to recognize that this is an aromatic or an arene. Okay, I'm going to move through these fairly quickly. Be able to recognize these structures. Alcohols have an OH. Ethers will have oxygen between two carbons. Make sure you can recognize the difference between aldehydes and ketones. Aldehydes and carboxylic acids often get confused. The carboxylic acid will have an extra O here. Difference between an aldehyde and a ketone, the carbonyl carbon is bonded on both sides by carbons with a ketone. It's bonded on one or both sides by hydrogens in an aldehyde. Okay, here's carboxylic acids. Derivatives, okay, if I showed you a picture of one of these, be able to name the functional group. Okay, same way with these nitrogen compounds. Okay, these are nitriles. I also included sulfur compounds, thiols and sulfides and disulfides. Okay, so let's move on to chapter 3. Okay, this is the general formula for an alkane, CnH2n plus 2. Again, be able to name the first 10 alkanes. This is a repeat of the idea of constitutional isomers. Be able to name alkanes using the IUPAC system. The longest chain is the parent compound regardless of how it's written. So in this case, the longest chain is hexane, not pentane. Okay, make sure you know all of these common alkyl groups as substituents. Okay, be able to recognize them. Okay, if the same substituent occurs more than once, we use a multiplier prefix. So here we have 3 methyls, so we would name this as 2,5,7 trimethyldecaine. Okay, every substituent gets a number, even the same substituent on the same carbon. Probably won't have too many, probably one at the most, complex substituents. Okay, but be aware of how to name those. Okay, so here's an example of where we have the same substituent on the same location. So we have 2,2,3,6 tetramethyl. Okay, this is an isopropyl group up here at the top. Okay, as the number of carbons goes up, the boiling point also goes up. Branching lowers the boiling point as is shown in this chart. Okay, I might ask you a few questions about petroleum refining. Alkanes are obtained from petroleum and natural gas. The principal method by which the products are separated is fractional distillation, which separates compounds based on boiling point ranges. Okay, none of these are pure compounds. They're mixtures within a certain range. Cracking is an important part of refining. It breaks large molecules into smaller ones, usually to get more gasoline. Okay, conformations. Conformations are the result of free rotation about single bonds. And for ethane, the two main conformations are staggered and eclipsed. This is a staggered conformation. Okay, be familiar with drawing Newman projections, which is what we have on the right. Okay, so these are the four, or actually two of the ethane conformations. We have the eclipsed and the staggered. And then this shows the energy. The eclipsed has the highest energy. There's torsional strain because these two hydrogens are repelling each other. Okay, this is how you would draw propane in the Newman projection. We're sighting along this bond between 1 and 2, so we replace a hydrogen with a CH3. For butane, okay, we have two more conformations. We have the gauche, where methyls are 60 degrees apart. We have the fully eclipsed, and then anti, which is the most stable. Okay, this shows the steric strain in the totally eclipsed conformation. We have a lot of repulsion between these two methyl groups. Okay, be familiar with cycloalkanes, how to name them, how to name substituted cycloalkanes. Okay, these are some examples of cycloalkane nomenclature. If the parent compound is larger than the cycloalkane is named as a substituent. In this case, cyclopropyl, cyclobutyl, and then this last one is cyclopentyl cyclohexane. Okay, you can have geometric isomers with cycloalkanes, cis and trans, and these are a couple ways that we can represent cis and trans. Okay, with a perspective drawing like this, or with the dashes and wedges. Wedges indicate groups coming forward, the dashes going back. Okay, so to go from cis to trans, we actually have to break a bond here and then reform it. Okay, be able to explain angle strain and torsional strain. Okay, angle strain occurs when there's a large deviation from the ideal bond angle of 109.5. This is especially prominent in cyclobutane and cyclopropane, the 4 and 3 membered rings. Okay, when all of these carbons are coplanar, you have eclipsing, and so that will produce a torsional strain here. Okay, here's cyclopropane. Unlike cyclobutane, cyclopropane cannot fold, and so it is especially it's especially energetic, more reactive than other alkanes and cycloalkanes. You have this bond angle strain, and then the hydrogens, these hydrogens have no choice but to be eclipsed. Okay, so there's torsion along this bond, and then there's distortion because of the bond angle.
I wanted to ask, in the case of cyclopropane, what is it mostly used for?
At one time it was, I'm not sure if it's still used for this, but at one time it was used as an inhalation anesthetic. Cyclopropane does occur in nature, but it's uncommon because of the high bond strain. Okay, this is the envelope form of cyclopentane. Okay, be familiar with that. Be familiar with how to draw a chair and recognize axial and equatorial positions. Okay, this is the boat. And with the boat, everything is eclipsed. And you also have some torsional strain because of the flagpole steric strain because of the flagpole hydrogens. Steric strain because these are not on carbons directly attached to each other. Okay, general rule, as far as axial and equatorial, there's more room in the equatorial position. And so that means lower energy, less repulsion. Larger substituents such as the terbutyl and isopropyl will especially favor the equatorial. Okay, if we have two methyl groups that are both axial at 1,3 positions, there's a lot of steric interaction. But when they're both equatorial, we don't see that. Okay, here we have a methyl and an ethyl. Okay, the form that's favored is where the ethyl would be equatorial, since it's a larger group. Okay, and then be able to name and recognize bicyclic and spiro systems. Bicyclic systems have two fused rings, that is, two rings sharing two carbons. And the way that this is named is bicyclo, and then in brackets 4. Okay, if we go across this way, we cross 4 carbons to go from one bridgehead to the next. If we go this way, we cross 2 carbons, and then if we go this way, we cross 0. So it's 4, 2, 0. You need 3 numbers. This is what's called a bridged bicyclic. Okay, this going this way, we cross 3 carbons going from one bridgehead to the other. We cross 2, and then we cross 1 going this way. So it's 3, 2, 1. And then the last part of it is the total number of carbons. Okay, if you add these up, 3 plus 2 plus 1 is 6, plus 2 for the bridgehead gives you 8. So that's where we get the octane. And okay, spiro compounds. Okay, I didn't see a slide with the spiro compound. This is the last thing I'll talk about. Okay, spiro compounds will share 1 carbon, like that. Okay, so this would be named as spiro bracket. And then we cross 1, 2, 3, 4, 5. And then if we go this way, we cross 2. So a spiral will just have 2 numbers, and this would be octane. Okay, 5 plus 2 plus the shared would add up to 8. All right, so that's it for today. And I'm going to go ahead and end the meeting.
I had a quick question about the.
Yeah, go ahead.
So in the Friday lecture, I think it was, you mentioned something about the homework, and so I was confused. Are we being graded on the homework, or is it just something that we're supposed to do supplementally? What's
Mastering? Yeah.
Say
Yeah.
again? Sorry.
Yeah, you are.
Okay. We are being graded on that. Okay. So the things that I saw that looked like they were assigned in Top Hat, were those actual homework assignments that are being graded?
No, they're assigned, but there's no credit.
Okay, so has there been any homework assignments that have been like assigned for credit?
In Top Hat?
Just in general.
Yes. Mastering Chemistry has.
Okay, where can I find where to turn that in, and can I still turn it in for credit?
It's on Canvas. Mastering Chemistry is on Canvas.
Okay, and am I still able to turn it in for credit? Because I have not gotten any notifications from any of my school anything about these homework assignments.
Oh, I did send out an email a while back that was posted.
Okay. Is it past due, or when is it due?
I can adjust the due date.
Okay,
Yeah,
cool.
It is past due, but I can adjust the due date.
Okay, and it's just on Canvas. Is it under modules or files or?
It's under. Let's see. It's Macmillan Learning, or not Macmillan Learning. It's it should be under assignments.
Okay, cool. In that case, I'll try to get that filled out and turned in tonight. Okay, thank you.
Welcome.
All right, bye.
Dr. Trump,
Yeah.
so one more thing, right? For the master in chemistry, although you said it was written that it's due on 12, the thing shuts down at 11.
Oh, okay. I think what it does is it defaults to Eastern time. So I'll have to go in and fix that.
Okay.
Yeah.
So there's one on there that was due last night, and then there's one that's also due tonight. But the
Yeah.
one that was due yesterday looked like something that you didn't actually assign to us, and that it was something that like generated through that thing. So do we have more than one that's due?
Yeah, let me take a look at that. Okay. Yeah, let me double check as far as the due dates. All right, I'm going to go ahead and end this.